Thank you for your presentation. So, my name is Pablo Gimeno. I'm a PhD student at ViVoLab Research Group at the University of Zaragoza, Spain. And today I'm here to introduce our paper entitled Unsupervised Representation Learning for Speech Activity Detection in the First Step Challenge 2021. This is a joint work with my colleagues Alfonso Ortega, Miguel, and Eduardo Lleida. This is the outline for today's presentation. I will start first with a brief introduction to the topic, to the SAD task and the unsupervised representation learning paradigm. I will then comment a little bit on the context of this paper, the First Step Challenge, and the different tasks proposed. Then I will move on to our proposed SAD system for this challenge, with the main novelty of the unsupervised learning features. Then, in the last part of my presentation, I will explain our experimental setup with our data description and the metrics used in the evaluation, to finally present our experimental results and some final conclusions. So, speech activity detection, also known as SAD, is a support block for many other speech-related tasks, such as speech or speaker recognition. As you can see here in the figure, the main goal of speech activity detection is to accurately capture audio fragments containing a speech. Historically, we've seen a large number of approaches applied in the SAD task. Here I'm citing only some of them. For example, we can see some energy-based path or some based on the long-term spectral divergency. Focusing on the statistical approaches, we've seen GMM models or some models relying on specific acoustic features. And in the recent year, we've seen the deep learning taking the current state of the art. And this is the approach we've been using in the last few years for the First Step Challenge, and the one that we'll be using in this paper. As a novelty in this paper, for the SAD task, we introduced the use of unsupervised learning. We've seen a lot of unsupervised learning in this interspeech, and as you probably know, the unsupervised learning solution are here in order to alleviate the need for labeled data. Also, historically, we've seen an evolution on the different approaches to the unsupervised learning. First solutions were based on minimizing on reconstruction error, like the autoencoder application, for example. And more recently, we've seen the use of pretext tasks that aim to solve prediction as a classification. In our paper, we use a contrastive loss that, as you can see here, tries to choose an unseen fragment of the signal among other randomly selected distractor fragments. So, moving on now to the context of the paper, I need to introduce the First Step Challenge. In this paper, we present our submission to the SAD task for the First Step Challenge Phase 3. The audio in this challenge is coming from Apollo space mission, which is a really challenging domain with a strong degradation and different kind of transmission noises. In this phase for this year, in Phase 3, the focus was made on the system generalization capabilities, introducing a number of varying channels and new vision data in the evaluation subset. Taking all this information into account, our proposal for this challenge this year was to apply a deep learning solution based on convolutional recurrent deep neural networks. And as a novelty compared to our submission to the last year challenge, we are using a supervised feature learning to map new features from the raw waveform and apply them to a SAD neural network. So I will now move on to explain in detail our proposal for the SAD system, and I will start with the unsupervised representation learning. As you can see here in the figure, we have two main elements. We have a convolutional neural network encoder here in blue, which is a strided CNN working directly on the raw waveform, which is then the output of the encoder is then fed to a bidirectional gauge recurrent unit. Note here that it's a bidirectional because this is important in the contrastive loss. We are using the context, the CT vector in pink there, to predict 8 time steps forward and backward. We are using the forward and the backward element of the context to predict in both directions, using a contrastive loss as I have just explained. So finally, our representation is this pink element here which is a representation of 1024 dimensions that, after the unsupervised system is trained, will be used as a feature for the SAD system. Okay, now we'll explain the SAD neural network that we are using. The neural architectures that we are using in this paper are basically inherited from our previous experience in the challenge, from our participation in the last year submission. And as you can see in the figure, we have three different A, B, and C, which share a common recurrent neural network block based on a bidirectional LSTM. Then this is followed by a linear layer and a softmax activation that maps the output of the bidirectional LSTM to a speech score between 0 and 1. The difference then in the three neural architectures we are using is in the first blocks. We have three different blocks that we are alternating to obtain different architectures. We have one block that is based on the 2D convolutional convolutions. We have a second block that is based on 1D convolutions, and we have a third block that is based on the fusion of both 1D and 2D convolutions. As I explained earlier, in this paper, our novelty is the use of unsupervised learning features, and in order to be comparable with our previous submissions, we are also training this SAD neural network with some traditional Mel features. As you can see here, namely they are 64 log Mel and the energy concatenated to the input. We will compare this to these new unsupervised learning features. Okay, moving on now to the experimental setup, I will briefly describe the data we have used for training all of our systems. Focusing on the unsupervised feature learning approach, we are using around 130,000 hours of audio coming from different English datasets. You can see here some of them. We have LibreSpeech, RSR, Tedlium. We have a huge variety of data, but we have focused only on English data. For the SAD neural network, we are using only the data provided by the organization for the Fearless Step Challenge, which is composed of three different partitions. The train partition, which is around 62 hours of audio, and we will reserve 10% of that for training validation. Then we have development and evaluation subsets with 15 and 34 hours respectively. We will use development partition to obtain the optimal threshold and fine-tune our systems. And the evaluation subset will be used to rank participants in the final leaderboard. It also should be noted that the Fearless Step Challenge follows an open condition training, so any kind of data could be used in the training of the system as long as it is cited in the description. Concerning the evaluation metric, the detection cost function is used, the DCF, and as you know, DCF needs some kind of weights for both the false negative and the false positives. And here the organization is using 0.75 for the false negative and 0.25 for the false positives. So false negative errors are considered more important than false positive errors. Okay, so now I will move on to explain our results. In order to get a first intuition of how our unsupervised features are working, we wanted to obtain a representation of these new features compared to the Mel features. So here in this figure, what you are seeing is a TSNE 2D projection of the validation subset for both set of features considered. You can see here in the left you see the Mel features, and on the right you can see the new unsupervised feature. For the Mel feature, we can see a huge overlap between the speech samples and the non-speech samples, whereas in the unsupervised feature, the speech and non-speech samples can be separated much more easily. We can also observe in this unsupervised feature that they are merged in some subclusters, which we believe, our intuition is that this is motivated by the introduction of the gate recurrent unit in the unsupervised learning system, that is introducing this kind of temporal context, so that these little subclusters you can see here maybe for samples that are close in the sequence. So after we validated qualitatively our results, we also train both SAD systems with the Mel filters and the unsupervised filters. What you're seeing here in this table is the development and evaluation DCF for both filter for the as input. And this is also a summary of some of our best submissions with different SAD neural networks. I will first focus on the Mel filters. You can see here that we have competitive results in the development partition with all the numbers below 2% DCF. However, when we switch to the evaluation partition, we observe a huge mismatch between the development and the evaluation, with numbers around 8% DCF. This was somehow expected by us because we knew that there was some new channel data in the evaluation setup, and this was likely to happen. When we introduced the unsupervised filters, these are the results we obtained. And we can immediately see that we obtain a huge improvement in both the development and the evaluation subset. However, this improvement is more significant in the evaluation subset, with numbers that are around 3% DCF. To sum up, we can observe here a significant reduction in the mismatch between development and evaluation partition results. Okay. In this table, I'm now summarizing some of our best submissions to the Challen compared to the organization baseline and the challenge best submission. As you can see here, we largely outperform the organization baseline, and we obtain pretty competitive results. We were close to the challenge best submission, but we finally ranked third among all teams in the SAD task. So to sum up my presentation, in this paper, we introduced ViVoLab submission to the SAD task of the Fearless Step Challenge 2021. As a novelty, we explore the use of unsupervised feature learning in the SAD task, and our experimental results suggest that this kind of application provides a more robust representation, even if in shifted acoustic conditions with different channel and varying data. Finally, we obtained competitive results, and we ranked third among all the participant teams. So that's the end of my presentation. Thank you for listening, and if you have any questions, I'll be glad to answer them.
All right. Any questions from the audience?
Either online or in person. We're monitoring the online chat, so if you got a question, yes, go ahead. Wait for the microphone.
Thank you for your presentation. Really interesting results. So you did your pre-training on a lot of different data sets, but what kind of data would you like to have actually to maybe close the gap further?
I know that there's a lot of data available for the Fearless Step Challenge, like there's a huge data set. We were thinking on using that because we know that maybe using the same domain for training in the unsupervised feature learning would be interesting. But at the time of the challenge, we didn't have that available. So we were training on we thought that maybe using the same language as in the Fearless Step Challenge would be the closest thing we had. But yeah, I think the next step here would be to use all the data available for the Fearless Step Challenge, to use a pre-training in the unsupervised feature learning, and then use that for the SAD.
So if I could follow up with a question. I know for the Fearless Steps Challenge, there's 100 hours that's released with that data set, but you do have access to the full 10,000 hours for Apollo 11, but it's all unsupervised, right? So but that's part of your advantage here. So you can bootstrap this new data to kind of help improve your system. If I can ask one quick question, in your training you noted you used 130,000 hours of audio from English data sets. Did you make any attempt to try to emphasize male speakers in that? Because most of the, not all, but most of the audio on Apollo 11 for the mission control people are male.
That's not something we thought about, really. It's interesting. I mean, it could be interesting in our next steps, but yeah, we didn't thought about that.
It doesn't work for all the channels because public affairs channel actually has commercials and all kinds of anyone talking, so it's much more random and difficult.
Okay, thank you.
Other questions from the audience? Yes, we have one in the back.
Thank you for your presentation. I actually do not know all the data sets you've used for unsupervised representation learning, but the ones I know do not actually contain non-speech parts. It's only speech parts there. So when you're actually training on those data, which is completely speech, and afterwards you're using it to actually discriminate between speech and non-speech, what you show in your graph with red and blue colors is actually showing that the blue ones are actually out of distribution points, right? You do not see those points, these kind of non-speech points, in the unsupervised training.
So you mean in the Mel features or in the unsupervised features?
In the unsupervised features.
Uh-huh.
Since you're training on only speech, and then you're actually embedding non-speech parts, which are here the red ones.
So you mean that the system is only like discriminating speech and the rest is not trained or something like that? You mean?
In the data sets you showed for training, there are no non-speech data, right?
Uh-huh.
It's Libre speech, common voice. It's only people speaking. No
I see
silences.
what you mean. Yeah.
So don't you think that your model here is pretty effective because he actually puts out the point that he hasn't seen in the training?
My intuition for that is, even though those data sets contain mainly speech, then you have another neural network, like the SAD neural network, which is trained specifically to recognize the speech and the non-speech fragments. So even though the unsupervised features are like trained mainly on speech, then you have another specific neural network that will focus on like discriminating this part is speech and this part is not speech. Like the unsupervised features are only working at the first level, like capturing the relationship between data, and then you like train a specific expert neural network to focus on the speech and non-speech separation.
Okay, thank you.
All right, I have one question too. So I understand that the idea or the goal of the unsupervised representation learning is to not basically enforce anything that goes to the network or to the classifier. But did you consider what could happen, or could you try basically feeding in the Mel-filterbank energies rather than the time domain signals as an input? Could they maybe, you would be basically learning different type of features, but could it be helpful at all?
Well, we didn't thought about that, to be honest, but it would be interesting to try, yeah.
It's again not fully unsupervised anymore,
Yeah.
but you're again extracting something from something that we know works very well.
Yeah. You're right. We'll think about that. Thank you.
So let's thank the speaker again.